for like Halloween or something.
Dude,
I don't know
oh
if you
my
can walk
God.
around with blood stains on the armor, like fake blood on the armor, because that would still look pretty bad to walk around in
True.
on campus.
Depends on how much blood you have. Really.
True, yeah.
All right, let's get started. And today we're gonna talk about elliptical galaxies. And I ran out of time to go through the reading, so you guys have a bunch of questions about galaxies and stuff that are still in the reading that I haven't gotten all the way through yet. I've gone through some of them, but I haven't gotten through everybody. So if you have a question that you left in the readings, and I get to that point, feel free to ask. Yeah.
A quick question from like the reading before last.
Yeah.
You said that we could see like a web of dark matter. How do we even identify that?
Oh,
like,
yeah.
See that's
so,
how it is.
Well, so the primary way you see how it is simulations. But if you look carefully at the galaxy distribution, you can see it statistically. And also you can see it here. Let me actually pull up. Oh, let's see. The best way to see it is in the 2-degree field. So let me see if I can pull up the best measurement of it. Where do I have it? I know where I can find it. Sorry. I know the picture that I want. I just need to remember which slide deck I put it in. And if it's even in this year. So because that's a great question, and I should have put some stuff up already about that. So the web of learning, or of the web of the galaxy looks like this. And let me see. If there was internet here, I could just pull it up because I know exactly how to find it. I just have to remember which one it is. There's the cosmology. Nope. No. Where the hell did I put it? I gotta go way back in history.
Oh, yeah.
Here it is. Okay. All right. This is why. So this is the 2-degree field. This is a galaxy redshift survey. This is a 3-dimensional map. So, okay, astrophysics, it's hard to get 3 dimensions, right? We got 2 dimensions, and then the 3rd dimension is difficult. How far things away is hard. Where they are, left or right, that's pretty straightforward. That's a knob on my telescope. So what they did, and this is actually pretty old. This is from the early 2000s. And this image is, and maybe, was it this one? Yeah, one of these images of this galaxy web is one of the first things that really sparked my interest in simulating astronomy when I was in undergrad. I saw this cool talk on how they can make, and this is in the late 90s, so all this stuff was still pretty green, but they were making computer models of this. So what are we looking at here? This is the galaxy distribution on a wedge of the sky. It's about 2 degrees across. So there's one that's pointing out that way and one that's pointing out that way because we want to make sure that the universe is basically the same in both directions, right? So they measure the position and the redshift, and the redshift gives you the distance to a whole bunch of galaxies, and they see that it makes this kind of fluffy filamentary pattern. It looks like a foam. Like there's elongated skinny structures, there's like fluffy structures, but there's a lot of like fibrous long skinny structures. This one here is called the Sloan Great Wall, and it kind of stretches from here to here, and it's one of the largest objects in the universe, if it's really an object. Sometimes things are together and you don't know if they're together because they happen to be there or because they're buddies. So if we see a whole bunch of galaxies that are kind of close together, it's hard to say if that's a real object or if it's just things that happen to be there. Kind of like looking at constellations in the sky. A constellation isn't a real thing, they just happen to line up that way. So it's probably a real thing, but it would be just enormous. So each point in this is a galaxy. So this is like buttloads and buttloads of galaxies. But here's where we see this filamentary structure. And you can see it better when you look at, now I'm hoping that I was kind to myself and left the things the way I wanted them. So if you do a simulation, so we understand what the early universe looks like. Nope. Here it is. It's under galaxy formation. So all the stuff that I'm gonna talk about later. Here it is. Okay. So actually, I'm gonna full screen this guy. So we understand what the high redshift universe looks like. So at the beginning of the universe, everything was flat and boring and nothing was happening. And we can see that it was flat and boring in the cosmic microwave background, which I think we're going to talk about next once we finish talking about galaxies. Then we'll talk about cosmology. I usually don't do it in that order, but I'm going to try it in that order because that's the way it is in the book. Usually I talk about galaxies and then I keep talking about galaxies and then I talk about cosmology, but I think I'll do it in the book order this year because why not? So we understand what the universe looked like at a redshift of like 1100, or a redshift of 1000. So that's way back in the history of the universe. It's flat and boring with these little ripples in it. So we start with that and we let those little ripples grow and it does this. So what it does now statistically, if you do a high resolution version of this so that you really know what you're doing and you're really careful, this forms, you can see this is a filament. This just is showing the galaxies, but if you add the gas too, you can see that it makes these stripy filamentary pictures. Yeah, we'll talk more about that when we get to cosmology, but it's kind of awesome. All right. So this bimodal distribution, this is a thing that this is where I'm going to start today. Any other questions before I get started? And new stuff. So I'm going to finish up galaxy classifications. Talk a little bit about this bimodal distribution just because it's important. Then I'm going to talk about I write things down so that I can forget them. Then we're going to talk about genes and freefall. So we'll talk about some basic physics for a little bit. Then we'll go through elliptical galaxies, and then we'll talk about the relaxation. So the relaxation section in the reading is confusing and weird, and a lot of people get confused by that. So I'll go through that today. Even though it's this long, complicated derivation that he then says doesn't really work, but it's still a useful derivation. So we'll go through that. Okay. There's a reading up for a little ways. There's another reading coming up next week and then another one after that. I just put that up. That covers galaxies, so that's the end of the galaxies section. There are 2 homeworks up that I just put up. I think I posted both of them. Oh, did I post both of them? Does anybody have their phone out? Did I post? I posted both homeworks? Okay, good. Sometimes I forget to hit actual publish on the thing. So there's 2 homeworks up. There's a paper one that's not long, but not easy. So be careful and go through the problems carefully. It's not super long, but a lot of people get hung up on some of these problems. And then a numerical problem, which similarly isn't long, but if you're new to programming, then it might be challenging. It's write one function that's a black body. It's not particularly complicated, but if you're new to programming, it's not something that you necessarily know how to do. So we'll have office hours for both of those, which I do hope if you need them, you attend. Okay, so we'll finish up the color. So I talked about this this 2-dimensional histogram here that shows where galaxies are. And now this isn't, so when they made this plot, the important thing about this plot is that they did not first mark which ones were spirals and which ones are ellipticals. Because that's actually really hard to do for a 500,000 galaxies, because you kind of got to do it by hand, or you got to use some machine learning tools to help you identify things. And that's machine learning is now a tool that you could just use. It's not like a magic box anymore. So you can classify galaxies, but this is not. This is just their colors. And we learn a huge amount about their colors, but it doesn't tell us which ones are spirals and which ones are ellipticals. But it does tell us what the colors are. And the color is a good indication of whether it's a spiral or elliptical. I will tell you why in a couple of classes. We'll talk about star formation. The star formation in the galaxy really sets the colors of the galaxy. If there's a lot of stars, there's a lot of young stars. If there's a lot of young stars, it's blue. If there's not a lot of young stars, it's red. Seems like a really overly simplistic way to classify things, but that's what we do. So the redness is the vertical axis, and so we have a big blob up here of red galaxies that are bright, big blob down here of blue galaxies that are less bright. There's galaxies in the middle too, so this stuff in the middle is called the green valley. It turns out there's a lot of stars. There's a little bit of star formation in these, but these are probably where all the S0 galaxies are coming from. So if you remember back at our tuning fork, we've got elliptical galaxies, and these are round dudes, and we got spiral galaxies, and these are flat things, and then we got these flat things that kind of look round. Ellipticals don't have any star formation, and spirals do. We got these things that look kind of like spirals, but they don't have any star formation. They don't have much gas. So it's not clear if they're spirals that have just eaten all their gas and are about to turn into ellipticals, or if they're spirals that haven't started forming stars yet. So it's not really clear where these things sit in the galaxy evolution. What's an S0 galaxy? Those tend to be in the green valley. Okay. And from simulations, you can see that things. Oh, the other thing. So how can I tell if something is a elliptical or a spiral? Well, I've got to look at the distribution. So I'll come back to this in a second. So there's this thing called the Sirzik profile. You don't have to remember what this is right now, but it's a generic way of generalizing the profile. So I talked about disk galaxies, and disk galaxies are exponential. So the light in whatever units, as a function of radius, goes like e to the minus r over some scale height h. So that's for spiral galaxies. But for elliptical galaxies, we have a different profile that I haven't talked about yet, but it kind of goes like the lower one, e to the minus r to the what? 4. So this is e to the minus r, and this is e to the minus r to the 4th. So if we can just sort out how this thing behaves, then we can kind of grade things into whether or not it's an elliptical or a spiral, just based on fitting a curve to its light distribution. Not looking at it, not saying, oh, this is a thing, it's got 4 arms, but by just saying, I'm just going to measure stuff. And you can see so you get this Sirzik index, which will make more sense once I describe what Dirac-Galois is. But you can plot these in a 2-dimensional histogram again. So this is the Sirzik index n, and remember 1 is an exponential, and 4 is this Dirac-Galois profile that I'll talk about in a second. And you can see that this is again u minus r. U minus r is a color, bluer is to the left. So all of the things down here have low Sirzik indexes and are blue, and all the things up here are red and have larger Sirzik indexes. So why do I care about this Sirzik index? Let's jump into let's sprint through the elliptical slides. Where did I open them all up? Yeah, here you go. Okay. Okay, so come on, where'd you go? Okay, so there are a number of kinds of elliptical galaxies, and there are once again tables in the reading that I would like you to spend a minute with and like look at the numbers and get a feeling for how these things behave. So what are the masses of these objects? So the masses of like an S0 galaxy is like 10 to the 10 or 10 to the 12. Mass of a solar masses. The mass of a CD galaxy is like 10 to the 13, 10 to the 14. So that's like an order of magnitude or two larger than the Milky Way. Your standard ellipticals are smaller than to larger than the Milky Way. 10 to the 8 solar masses isn't very big. 10 to the 13 solar masses is a little bigger than the Milky Way. And we have these dwarf ellipticals and dwarf spheroidals that have masses of like 10 to the 9 or 10 to the 8 solar masses, which are pretty little objects. We're not going to worry too much about those, but we'll talk more about them when we get to cosmology problems. Okay, so we see that they're red, and this implies that there's no active star formation. And I'll go through in detail how color relates to star formation in a little bit, but the short answer is, like I said just a second ago, if there's star formation, then there's young stars. Young stars are blue and big and massive and bright. And they don't live very long, so after they're all dead, then the galaxy that's left over is all the little stars that are redder, that aren't as hot, that don't burn as fast, that hang around for longer. So you get like your K stars and stuff. That's what makes up an elliptical galaxy. The gas is very hot. The gas is like 10 to the 7 Kelvin. That's like 10 million Kelvin. And there's very little neutral hydrogen or molecular hydrogen. Now, these all are related to the fact that they're not forming stars anymore. So hot gas is really the reason that there's no stars anymore. So the gas in an elliptical galaxy is all hot, and the reason that it's hot, and it is hot, therefore it cannot form stars. So I'm going to derive in a minute, I'm going to derive something called the Jeans mass. And this is, to put really short, if I have a gas with a temperature T, which here the temperature is hidden in the sound speed, the temperature T and a density rho, then that thing will break under gravity into chunks about this size. Put more realistically, or more accurately, this is the smallest thing that can form this is the biggest thing that can form that won't collapse. Anything bigger than this certainly collapses. So this is the typical scale of how massive a blob of gas can be to collapse. And I'll show you where it comes from. It's basically pressure pushes out, gravity pulls in. You just relate those two time scales and you get a size. And it's about, so this, this format is of writing things down. Astronomers like to do this. Chris McKee really likes to do this. This format is a funny way of looking at things, and I'm just going to talk about it for a second. Because you'll see it a lot, and until you're used to reading it, it may not make much sense. So what we say is that the Jeans mass is a function of the sound speed and the density, or the temperature and the density, because the temperature and the sound speed are related to each other. The Jeans mass is some number times how it behaves with variable 1 relative to fiducial 1 to the power 1, and then other variables, variable 2 over fiducial 2. What does fiducial mean?
Comparison?
Yeah, fiducial means the thing that I'm comparing everything else to, or the thing that I'm comparing to. So it's like your standard. It's like your I don't know. Basically, it's the thing that I'm comparing it to. So lots of things behave like power laws in astrophysics just because there's a lot of chaos, there's a lot of random processes, there's a lot of stochastic processes, there's a lot of things that make things feel like power laws. So we try to pack everything into a power law. So when you have a formula like this, you say, I've got M of, for instance, C and rho. I'm going to pick a fiducial value for this and a fiducial value for this and evaluate it. And that gives me the number that's out front. So this is the Jeans mass of, let's call this C hat and rho hat, where C hat and rho hat are 10 Kelvin and 10 to the 3 centimeters. T hat. Sorry. So I have my function for the Jeans mass, which is like, okay, the C sounds cubed pi over 6. C sound cubed over the square root of G rho. This is equal to, the sound speed is equal to the temperature to the 3/2 times K over M. So I'm going to go between sound speed and temperature without thinking about it, because they're the same. So I have my function, which is this. So I just evaluate my functions and my fiducial values, and that gives me this. So the Jeans mass at 10 Kelvin and 1,000 particles per cubic centimeter is 2 solar masses. Make sense? Then this gives me the scaling too. So if I want what the Jeans mass for 100 solar or for 100 Kelvin gas is, what's that? How much bigger is that than 2 solar masses? You can sort that out just by looking at it. So I just plug in 100 here. Say I leave N alone. I just want to raise the temperature by a factor of 10. The Jeans mass is going to be 10 over 100 over 10, so that's 10 to the 3/2. 10 to the 3/2 is what? It's like 300, right? So this is going to be like 600, because it's like 10 cubed, which is 1,000, and the square root of that, which is like 300. So we got 300 times two solar masses. It gives me 600 solar masses. So this kind of format is really nice for understanding how a formula looks. The formula on the top is hard to understand because it's kind of complicated, but writing it in this fiducial and then the power and then the parameters is a really nice way to write formulas. Anyway, Jeans mass. Temperature goes up, Jeans mass goes up. Why? More pressure, more support. So if there's more support for from the pressure, then you can support a bigger object. Okay, so hot gas can't form stars is the upshot. When I have 1,000 solar mass, or when I have 1,000 or 10 million Kelvin gas, the Jeans mass is thousands of Kelvin. So, or thousands of solar masses, and it's hard to get 1,000 solar masses in a spot to all collapse at once without it doing something weird. Yeah.
How like spread out can this be? Because like obviously the whole universe has like a mass. Like does that mean the whole universe is gonna like, collapse? Or like, oh.
I mean, the whole universe is collapsing and also expanding. The expanding is what keeps it from collapsing already.
But like in a given like just cloud of dust, like how far apart can that dust be? Like, because if you have 10 solar masses of dust spread out over like a massive distance. Gotcha. Yep.
So it can only be spread out by this much. Mass is rho r cubed, so it can only be spread out by rho or by r because we know what the density is.
Gotcha.
That's a really good question. That's a good question. So like, how far apart are my 1,000 solar masses? Well, they're going to be set by the density of the cloud.
Okay.
So that sets the size too. So the Jeans length is really what we're going to derive, and then we get a mass out of that. Okay. So you get a size for the fluctuation. And we'll do it the cheap and dirty way. I'm going to derive this the cheap and dirty way in a minute, and then we'll do it the long way probably later in the semester. The long way is a lot harder, and you get the same answer. Modulo a factor of like pi. So okay, so the Vauquelin profile. Let's talk about this for a second. I just need to mess up for a minute. I don't think I need it. I want a monkey that erases the board before I start, but only the ones that I don't need again. I don't know how to make such a monkey. Okay. All right. So the de Vauquelin's profile is this thing at the top. So I of r This is the brightness as a function of radius. And it's a brightness per area. And do we have units on that? No, this is in brightness per area. There's several ways you can write it down. It could be in magnitudes per square arc second, or solar luminosity per square kiloparsec. This one actually has to be in solar luminosities per square kiloparsec because this is a brightness and not in magnitude. But it's light per area, whatever units on light and area you need. And what you find is that if you take the log of I of R over this effective brightness, which we'll talk about in a second, this equals some number minus 3 times R to the 1/4. Minus 1. So the log of I goes like R to the 1/4. That is what de Vaucouleurs profile looks like. So why do we have this profile? Where does that come from? It takes a second, so hang on a second. So if I have a sphere of gas, once again, there's a couple of places where I'm going to start with a sphere of gas. It has an equation of motion which looks like this. dv dt is minus the pressure gradients minus the gravitational acceleration. This is just F equals ma. And I've got A and is pressure and gravity. This gives me an equilibrium. If dv dt is 0, then I can just rework this to get a pressure equilibrium. And this has a bunch of solutions. So this expression here is actually important. dPdr, this is the pressure gradient, is equal to minus rho times g times the mass enclosed over r squared. And that, what that says is that the pressure is supporting the thing from collapsing. Now remember that we don't have actual stars, so this pressure is the energy per unit volume in the stars. That's okay. So there are a bunch of solutions to this. One of the solutions to this is rho of r equals some number including pi's that I don't care about over r squared. So I'm putting the pi's in quotes to indicate that they may not be really pi. But 1 over r squared is the behavior. So 1 over r squared. Everything in nature likes to go to a 1 over r squared because gravity likes to make that happen. When gravity's pulling in and pressure's pointing out and everything's basically relaxed, it tends towards a 1 over r squared kind of behavior. Now, what happens at r equals 0 with this density distribution? It's infinite, right? So that's clearly not great. So, okay, let's fix that. You got 1 over r plus r naught squared. Now I have a thing that has the same behavior, has the same 1 over r squared behavior, but has a hard inner core. When r is smaller than r naught, then this is flat. See that? Roughly. And when it's bigger than that, it falls off like 1 over r again. The other problem with this is let's integrate it. Let's integrate 1 over r squared. The integral of 0 to infinity of rho times dv. This is the total mass, right? This is just integrate the density over the volume. 0 to infinity of 1 over r squared. Now there's pi's and sigmas and stuff in here that matter, but I'm jumping past them because they just cancel out and they don't show me the problem. They're not part of the problem. 1 over r squared. What's dv? Let's say that r is the only quantity that I care about. What's the volume element in my integral? Almost. That's after you do the integral.
Oh, 4 pi r squared.
4 pi r squared. 4 pi. 4 pi comes from from the solid angle, so this is in steradians. This is the d theta and d phi integrals. And then I'm left with the dr integral. The d theta and the d theta integral gives me an r squared as well. So this is just what's left over from the fact that all my volume elements are these trapezoid things, and the volume element changes size as I move around, right? So the size of this is 4 pi r squared dr. Let's do this integral. What is this integral? I go 1 over r squared times r squared, and I integrate to infinity, I get infinity. Here you see why. The integral is just a constant times infinity space. So the other problem, so okay. Let me talk about singular isothermal spheres for a second. Do I have a board behind here? No, there's not. So the singular isothermal sphere, and there's a homework problem on this. So the homework problem, the book doesn't introduce this until, oh man, it's really hard to look over there and erase over here. The book doesn't introduce the singular isothermal sphere until galaxy clusters in chapter 6. So part of the homework is go read that section in chapter 6 and then do the math that's associated with it. But I'm going to talk about it now because I actually need it now. So this thing, the singular isothermal sphere, is kind of a bullshit cartoon, but is an extremely useful bullshit cartoon. So it is a sign of gravitational equilibrium. And what it is, it says that rho goes like 1 over r squared. Thereabouts. Clearly it can't go exactly like 1 over r squared because that A has infinite mass and B has infinite density at the center. So it's got to go like this. But, okay. But they're all over the place. So the singular isothermal sphere is a very useful tool for modeling things because rho 1 over r squared is really useful. Clearly it's not perfect. So there are other these solutions, like the King sphere, the Plummer sphere, which go like, instead of r to the minus 2, they go like r plus r naught to the minus 2, or this Jaffa solution, which is r to the minus 2 plus 1 over r naught to the minus 2, which gives you a similar kind of behavior. And it's also a solution to this equilibrium business. Now, what do I do with that? So I'm going to leave this singular isothermal sphere out because all those things are important. So what do I do with it? I then take my density and I integrate it along z. So I take this 1 over r squared and I make it along z. Yeah.
3 and 4, what are those?
That says infinite rho at 0 and infinite mass. So that's what it is, and that's the problem. So if I integrate one of these, now clearly if I have just 1 over r squared, this is going to blow up again. But this one only blows up like log z. But when I do this with one of these fancier profiles, then I get the Sirzik index, or the Debacke-Lotus profile. So this falls out of integrating. Wait, let me see. Is that right? No, it's not there. So the Debacke-Lotus profile. So you integrate 1 over r squared or something like that in z, and it gives you behavior like this. I haven't sat down to play around with these profiles a lot, so I don't have a great intuition for why this goes like the 4th power there. But this is an observational thing. This is a thing that people look out at the sky and say, this is what it looks like. And it turns out these are always associated with equilibrium kinds of structures. Okay. Where's my doer? Oh, it's way over here. Okay. So this is the projection of a relaxed object. That's the important bit. I want to talk about that now. This feels out of order, but I'm going to talk about it now anyway. So this is the relationship between the effective radius and the maximum brightness for a whole bunch of galaxies. So the effective radius is where half the light is contained within that radius. So we define the effective radius as the integral of 0 to RE. So the definition of this quantity is in the integral, which is a weird way to put it, a weird spot to put a definition, but that's okay. The integral of I with respect to R, and I think I need a 2 pi r in there because this is a 2D integral, right? Equals 1/2 of I total. Now, it's kind of funny because really this is the integral from 0 to infinity of I of R, 2 pi r dr. So I've got this quantity, the effective radius, that I'm defining with this integral and this other integral that looks basically the same. But why this works is if I look at how the light falls off, this is I and this is R, light falls off pretty fast. And what I want is, this is the total area, we'll say the radius where half the area is like here. Now the reason we do it this way is because I don't actually know observationally where the edge of the galaxy is. It could be here, it could be way over here, but none of this crap is contributing to the light. So it doesn't matter if I miss it. So when I define the effective radius as the half light radius, then it's a pretty robust measurement because it doesn't matter about if my measurement kind of sucks. If my measurement kind of sucks, I'll still get about the same answer for the half light radius. So this is the effective radius of a galaxy. It's not the actual like encompassing radius, but it's the effective radius versus the total brightness. So it makes sense that total brightness goes up with effective radius. Make sense? Bigger thing is brighter. Sound. And this is true, let's look at this graph again. This is true for all kinds of different kinds of objects. So this is the effective radius versus the brightness. And you can see it's an increasing trend for my big normal kinds of galaxies, and it's a slightly flatter trend, but it's still a positive trend for my little bitty dudes. Oh, here's another brightness plot that's in magnitudes. Is brighter to the left or to the right on this plot? To the left. No, to the right. Sorry. Which way am I looking? I'm looking at here, and I'm saying it's going that way. Sorry. It's going that way. So it gets brighter to the right. Negative 24 is brighter than negative 6. Bigger thing is brighter. Okay, weirdness. Here's a weird thing, though. The average brightness goes down with effective radius. So if I take the total brightness and I divide by the size, I get the average brightness. That goes down as things get bigger, which is not what you would expect. It's kind of backwards. You expect things to just get brighter on average and in general. It's because they get bigger faster than they get brighter. Bigger is less dense. This is an important fact. One of the things that this tells us is that these things merge. As they grow, they also grow in energy. Because the size of the galaxy is determined by its total energy. Remember, B squared equals GM over R. So if M is fixed and R goes up, that means V goes up. So the velocity and the radius are tightly related, or intimately related. So this is an important point that we'll come back to later. Okay. What sets the axial ratio of an elliptical galaxy? So some elliptical galaxies are real round and some are kind of elongated in one way or another. So what sets that? So, oh, I like these questions. Huh, thanks, pass me. Let's talk about velocity distributions for a second. So, what sets the axial ratio of this galaxy here? Why is it longer this way than it is this way? One answer, part of the answer is projection effects. If I have a football and I look at it along the short end, it's going to look round, and if I look at it along the long end, it's going to look like a football. So there's some projection effects that we can't get around, but there's physics that's setting, like if everything were actually round, then everything would look round. So clearly there's some elongation. Why are they elongated? So they're either elongated because either they're rotating and that rotation is flat, flattens things out, or they're just sitting there and they have an anisotropic velocity distribution. What does this mean? What does anisotropic mean?
It's not uniform.
Not uniform how? What property is not uniform? So you're right. It's not uniform in direction. Not uniform in position is homogeneous or inhomogeneous. Isotropic means it's the same in every direction. So I look this way, I see the same thing as if I look this way. Now you can be isotropic and not homogeneous. So if I've just got a star, if I were a good drawer, pretend all these lines are the same. If I'm sitting here and I look out anywhere, I see the same field of lines. So that's isotropic, but if I move over here, then I'll see something different. These are all radiating from this point. You can tell if you're sitting over here. So this is isotropic, but not homogeneous. I can make something that's homogeneous, but not isotropic if I just have one direction. These are the same everywhere, but if I look that way, that's different than if I look this way. Now, what are these stripes? Whatever. This could be density distribution, so the density is high along these directions. Clearly they're not homogeneous. They're round. There's a middle and an end. But the question is the Vy and the Vz distributions the same? So one of these two things. So let's talk for a second. And let's look at these questions. What's the distribution for something that's just sitting there? So let's think about this in two dimensions. So I've got a Vx and a Vz. So if my object is just sitting there and all of my particles are rattling around in some kind of circular orbits, then my Vx direction velocity will be the same as my Vz velocity. I'll have something that's basically round. So that'll look like this. So Vx will look like that. And Vz will look the same. Yeah.
So for isotropic, is it more dependent on like your reference point?
They both depend on the reference point and the direction you're looking.
Okay. But like for if it's uniform or like homogeneous,
Mm-hmm.
that depends on the reference point?
Yeah. So where you're measuring it, that's more depends on the reference point because where you're measuring it matters. So homogeneous is all of the reference points are the same. Isotropic is all of the directions are the same. Actually, let me write that over here. Because those are things that I use all the time. homogeneous is the same at all positions, and isotropic is the same in all directions. Okay, so if I have an isotropic velocity distribution, that means that they're going to be the same in all directions. So if I've got something that's round and my things are rattling around and they're doing the same in all directions, then clearly my velocity in one direction is the same as my velocity in the other direction because the stars are going out at the same distance. Now, if I have something that's rotating quite a lot, let's say it's rotating that way at x, say it's rotating this way, then I'll have some velocity in x that's shifted because there's some net rotation. So if it's rotating a little, then it'll be shifted by a little bit. If it's rotating a lot, it'll be shifted by a substantial amount. So if I have some bulk rotation, then my velocity distribution will be centered around that rotational distribution. And if I have just random motions, then it won't. So let's see, let's go back here. So here is, here's the measurement that actually shows that things aren't elliptical galaxies aren't flat because they're rotating. They're flat because there's more velocity in one direction than another direction. So does that make sense? So it's either flat because they're rotating. Now if they're rotating, okay, so we have this this relation that the book uses. This is the rotational velocity, so I actually measure one side versus the other and I take the difference and I measure how fast it's actually rotating, versus the velocity dispersion, which is all of the randomness. If rotation is what's giving you the eccentricity, then you have this relationship, v rho over sigma is roughly equal to this fraction. But what we find is that for v rho over sigma small, these are all small galaxies. So this says that the rotational velocity is roughly equal to the velocity dispersion. So that means that it's rotating about as much as it is randoming. But with higher, more brighter objects, the rotational velocity is really low. So this is the log. So log of something is minus 0.4. That's not quite an order of magnitude. But our rotational velocity is small compared to our random velocity. So the real answer is whether or not there's ordered rotation or if it's just all the random motions in the galaxy. And it turns out it's mostly the random motions in the galaxy. Vx is distributed differently than Vy and Vz, and that's why there's more length on that one side. So if Vx is broader than Vz, so Vx looks like this, then my galaxy is going to be like this, because my particles can go way out over here because they're going pretty far, so they can go way out over here before they fall back. Whereas in this direction, they're only going to go up here before they fall back because the velocity is not as large. So the velocity is not as large, so they don't go as far. The energy isn't as high, so they can't climb as far out of the potential well. So the energy isn't as high, so they don't go as far. I'm going to talk about 20 minutes. Projection matters. So I can take one object, and depending on how I look at it, it looks like a different object. So oblate is pancake, and prolate is football. And triaxial means all three axes are different. So in oblate, the two long axes are the same. In prolate, the two short axes are the same. And the third axis is long. So we have all kinds of different galaxies. So here's a cool paper from a while ago. where what they did was they took one galaxy and they measured the axial ratios of a bunch of elliptical galaxies. Then they took one galaxy and they threw it through a bunch of random projections. And they made a distribution of what the random projections look like, and then they compared it to galaxies, and they said, well, we can reproduce this distribution with one galaxy. We just look at a bunch of different ways, which is kind of fascinating. So the axial ratio only tells you a little bit about the galaxies, what this really comes to, because how you're looking at it really matters. Okay, so complex evolution. So they look relaxed. This is what we could come back to. Is an elliptical galaxy looks like it's basically a relaxed object. It basically has a Maxwellian velocity distribution. I'll tell you what that means in a minute. But they're actually pretty interesting. Actually, let me go back to that for a second. Okay, so, and I want to answer one question that I did read from the reading. So, you don't know what a Gaussian is? So a Gaussian is a function of x, and it's parametrized by mu and sigma. So this is a distribution of some variable, and it's got two knobs on it. This is equal to, I'm going to start in the middle, e to the minus x squared. That's the basic behavior, e to the minus x squared. But that has zero mean. E to the x minus mu, where mu is the average, over 2 sigma squared. This is what the distribution looks like. So it has a center at mu. So if I'm going to plot this, mu is the center. And then as I move away from mu, it's squared, so it's symmetric about mu. It's biggest where x equals 0. It falls off everywhere x gets bigger. So as x gets large, minus x squared becomes large and negative. E to the large and negative gets small. So this falls off like this. Goes off like that. Goes off like this. And it has some width that's given by sigma. And where do we get these things? We get Gaussians. Gaussians are great because they show up whenever you add up a bunch of random stuff. If x is the sum on random, then when I get x from a bunch of different places, and x is a bunch of random crap that all got added together, whatever that process looks like, a bunch of random crap gets added together and gives me a number. I make a distribution of those numbers. That's a Gaussian. Nature's kind of cool because this always shows up. It always comes out like this. If I have a suitably random process, it gives me a Gaussian. Not all random processes. They've got to be identical, and they can't depend on each other. So the random process can't have any memory of its process. So it's got to be really properly random. Then you get something that looks like this. So this isn't normalized. This is normalized by 1 over 2 pi sigma squared, all of this in the square root. Now this g, if I integrate g from minus infinity to infinity and I integrate g of x dx, this gives me 1. I need that because I'm going to do averages with this thing. I'm going to take averages of stuff. So when you take an average, you add everything up and divide by the number. The dividing by the number part is taken care of by the fact that this integrates to 1. So that's what a Gaussian is. And it is a symbol of it is a symbol of a relaxed, properly randomized process. When you have non-Gaussian processes, those are much harder to deal with. And velocities, each velocity component is a Maxwellian. So Vx, I'll skip the normalization for a second, is going to be e to the minus Vx. So if I have an equilibrium state in a gas, then the velocity in each component is a Gaussian. So Vx, so the distribution f of Vx is going to be 1 over 2 pi sigma x squared, square root of all that. This squared is inside the square root. E minus Vx minus Vx bar squared over 2 sigma x. And f of Vy is going to be 1 over 2 pi sigma y squared e to the minus Vy minus Vy bar squared over 2 sigma y. So the distribution in my x velocity is going to be a Maxwellian, or it's going to be a Gaussian. Distribution in y velocity is going to be a Gaussian. Both of these might have their own sigmas. That's what we mean by anisotropic velocity distribution, is the width of the velocity distribution for x is different from y. Yeah.
Is that sigma in the denominator of the e supposed to be squared, or?
Yeah.
Okay, thank you.
Yeah. Now, if sigma x and sigma y are the same, then I can write down the distribution for the total velocity, and this equals v squared times e to the minus v squared minus v, 2 sigma squared. This is a Maxwellian. This part is what makes it a Maxwellian. It's v squared in the front. So a Gaussian is the distribution we get for random processes if nothing weird is happening. My handwriting sucks, so I'm just going to say if it's normal. If nothing weird is happening, this means that the random process doesn't care about its history, doesn't care about the boundary conditions. So if it's properly random, then you get a Gaussian. And then v squared is a Maxwellian. This is what this one is called. So if my Gaussians have slightly different velocities in one direction than the other, then I have an anisotropic velocity distribution, and it's going to elongate the galaxy in one direction because things go further in that direction. Does that make sense? So the fact that they're Gaussian, mostly Gaussian, makes them look like basically relaxed objects. We have some indications that they have a merger history, though. So the fact that the density goes down as they get bigger is a clear indication that they form by things smashing into each other and getting dynamically hotter. The velocity dispersion goes up as things merge together. We also have boxiness, which I'm not going to go into it too much. You do a Taylor series on an ellipse and you can get something that's kind of square. Some things look kind of square. Some things look kind of round. It's all observational phenomena, really. Oop, goodbye. That's gone forever. Yeah, I don't care about dizziness and boxiness today. But we have lots of indications of shells and shocks around galaxies. And these are indicators of merger events. And you can see large magnetic fields in some of these shocked regions. Let's see. And the fact that they go down, the density goes down. Matters. Okay. Does anybody have any questions about elliptical galaxies? Mostly we talked about Gaussians because an elliptical galaxy looks mostly like a Gaussian. Okay. Let's talk about, I got 15 minutes left, 12 minutes left. Talk about two useful things. So, free fall time and Jean's length. So I'm going to talk about both of these objects. Or Jean's mass. So if I have a sphere, it doesn't really have to be a sphere, but it doesn't need to not be a sphere. And it has some density rho, and there's gravity. All I care about is the density, and there's no pressure. It's no K assumption. These densities are really low. The temperatures are really low. So we can ignore the pressure. If I want to know how long it takes for this thing to collapse, we can do the dumbest thing possible and do dimensional analysis. I haven't done dimensional analysis yet here, have I? I do it all the time, so I forget if I've done it or not. So let's do it. So I want something that's a time. From something that looks like gravity and something that looks like a density. So I need, so what are the units on G? What are the units on time? Seconds. What are the units on density in CGS? Grams per centimeter cubed. And what's G in CGS? Centimeters cubed per gram a second squared.
Well, I know it was something along the lines of that.
I gotta go through that every time I write it down in CGS. The way I normally write down, oh, this is something that, so when you need to use G for this class, was 1 over 233. And then the units, this matters, is in kilometers per second squared, parsec per solar mass. That's a weird ass units, but it works best because we often have v squared equals gm over r. And I'm gonna put, I want my velocity to come out in kilometers per second because that's the velocity unit that makes sense for things in outer space. I want my masses and solar masses, and I want my lengths and parsecs, which are kind of odd units, but they're the units that make the most sense. So G, I have to go through this every time I work out the units on gravity. I gotta do this in my head because otherwise I screw them up. So G has got to be multiplied by solar masses and divided by parsecs to give me as kilometers per second squared. So, and that jives, right? I've got 3 lengths, 1 mass, 2 time. 3 lengths, 1 mass. I should write that down. I'll actually write that down on all the tests and stuff. Yeah.
Is that exactly 1 over 232?
I mean,
Is that just enough?
to this many digits, it's accurate. There's more digits. I think that we don't actually know G very well. we have the combination of a solar mass times G to like 7 or 8 digits, but G by itself only to like 3. Because it's easy to measure m times the sun, mass of the sun times G. That's what we can measure. G by itself is hard. So okay, I've got seconds, I've got centimeters, grams, and seconds, I've got grams, centimeters cubed. And I want to get a time. So seconds equals G to the A times rho to the B. Now I'm just going to do algebra. Have you guys done this before anywhere? Sort of a little. All right. So I'm just going to plug in the units. All I'm doing is saying I'm going to multiply this to some power times this to some power, and whatever I'm going to do needs to get me a time. This process is easy to do and gets you 80% of the right answer 60% of the time. Both of those numbers were fictions. But it gets you pretty close. So you'll notice we're going to get the right answer. The only thing that we're off by is as a square root of 3 pi over 32, which I actually should know off the top of my head how big that is, but it's like 1. Like 3 times pi is like 36, right? No, it's like 9. So it's like 9. So this is like a half, right? My brain filled in 4 pi for pi when I was trying to do that in my head, because it does that. So this is like 9 over 32, which is like a quarter, which is like square root of that's like a half. So it's really close to the right answer. So I just write down some math equations. I got seconds to the 1 equals centimeters to 3a, grams to the minus a, seconds to the minus 2a, grams to the b, centimeters to the minus 3b. And now, this is nice because now I have written down 2 equations, even though it looks like just 1 equation. I have 2 equations. No, I have 3 equations. Because centimeters and grams and seconds are all completely and totally independent quantities, so I can change one and the others don't care. They're linearly independent bases. So my seconds equation says that 1 equals minus 2a. My centimeters equation says that 0, no centimeters on that side, equals 3a minus 3b. And my grams equation says 0 equals minus a plus b. This is an overdetermined system. I have 3 equations, but only 2 unknowns, but that's fine. A is minus 1/2. B equals a. This one tells me the same thing. So I know that the time is g times rho times 1 to the minus 1/2. This is the free fall time. This is how long a blob of density rho takes to collapse. We got it there by dumb units. This is a really simple process. There's no physics in it. That's a lie. There's a ton of physics in this. It's all physics. You're just looking at the units. How do the units have to relate? They have to relate like this. There's no other way for that to work. So the only thing we're missing is the 3 pi. So you have to invoke physics to get the 3 pi. Which I'm going to make you do for homework. You'll notice that I threaten that more often than I actually make good on it. Oh man, I'm sorry. I apologize to future you. I didn't move the camera over there. So anyway, you just have to listen to that. Okay. Do I have a minute? I got 5 minutes. I'm going to rip through this really fast. So the last thing I want to do is the free fall time. No, the Jeans mass, which is a similar kind of argument. So we can do this with Kepler's laws pretty easily, and we get basically the same answer. We can do the Jeans mass with this unit C way that I'm going to show you now, or we can do it with a full proper perturbation analysis on the hydrodynamics equations, which if I still have time towards the end of the semester, I spent like 2 whole weeks on it last year, and it was pretty successful, so I'll probably do it again later, but not today. So I got a sphere, and it's got some pressure, which means it has some sound speed. How long does it take for, and some size L, how long does it take for a sound wave to cross from one side of the cloud to the other side of the cloud? It's got a length L and a sound speed C. L over C. T equals L over C. This is the sound crossing time. How long does it take to collapse? Free fall time. So if the free fall time is shorter than the sound crossing time, what happens? So the sound crossing time, I missed a bit. Pressure waves even out density distributions, or density perturbations. So if I make a density perturbation in the air in here, which I'm doing with my hands, density right in front of my hand goes up by like 1 part in 10 to the 7. Sound waves carry it away. Pressure waves carry that away. I'm not going enough to make enough sound waves, but pressure waves carry that away. Pressure waves go at the sound speed. So if the pressure wave is too slow, it'll collapse before it can be supported, right? If the pressure wave is fast enough, then you make a little perturbation and it'll just wash out because the pressure will take care of it. So this gives me, I've got L over C is less than 1 over G row stored in the back. So we'll just put the C over here. This is a definition of the gene's length. And then L, this is LJ. LJ times rho cubed gives you the gene's mass. Remember, the gene's mass had a C cubed and this did a 3/2. It's the same answer. That's a really quick derivation. The other one involves a whole bunch of math. And it gives you, again, basically the same answer. And I'm going to stop for the day. Does anybody have any questions on gene's length or free fall time? Yeah.
Actually, for the gene's mass, if you have what would the other side be?
This?
Yeah.
So it would just be LJ, so we LJ times rho cubed. No, sorry. Why did I write it like that? Jesus Christ. LJ cubed times rho. You just cube this and you get C cubed over G to the 3/2, rho to the 3/2 times rho. And then the rho cancels one of those 3/2 and you get C cubed over G to the 3/2, rho to the 1/2. Which, do I have it up here? Here, the only thing I'm different by with this definition is a pi over 6, which is like a half. So again, we're good by like half. Any other questions on this stuff? Cool. I should put it back on the thing because that's here. I'm gonna put this. Here's the board that I skipped. Okay. Reading due, homework due. See you Tuesday. Have a good weekend.